Today we're breaking down how AI makes one of its most important decisions: classification. Every day, invisible algorithms are making split-second decisions inside the apps you use. For example, is this comment written by a bot or a human? Is this credit card payment fraudulent or just you on vacation? Is that smart home sensor seeing a burglar or just the house cat? Computers don't guess. They use a specific branch of machine learning called classification. And today, we're breaking down the three brains behind those decisions. In this video, we're breaking down the three core ideas behind classification. Number one, logistic regression, the math of how likely something will happen. Number two, decision trees, models that make decisions using simple if-then rules. Number three, ensemble methods. This is where we combine multiple models to improve accuracy and stability. By the end of this video, you'll understand the models that power recommendation systems in your daily apps, content moderation, and real-world AI decisions. And the wild part, one of these models is over 70 years old and still powers modern AI systems. At its core, classification is about making choices. More specifically, it's about putting something into the correct category. In many real-world problems, we start with the simplest case, binary classification. That just means there are simply only two possible outcomes. For example, spam or not spam, fraudulent or legitimate, yes or no, and the classic, true or false. We call one outcome the positive class, which is usually the event we care about. And we call the other outcome the negative class, which is the absence of that event. So the entire job of a classification model is simple. Given some input data, decide which of the two categories the data belongs to. To do that, we start with one of the most important models in classical machine learning, logistic regression. So let's talk about it. Imagine your smart home trying to predict, will the owner be home by 6 p.m.? It looks at past data, things like your GPS location, your commute time, maybe even traffic patterns and weather. Each past day becomes a point on a graph. Some days you made it home by 6 p.m., some days you didn't. The model's job is to find a pattern in that data. At first, it tries something simple. It looks for a straight line boundary that can separate the two groups of yes and no as cleanly as possible. But here's the problem. Real-world data is rarely perfectly separable. There's overlap, there's uncertainty, there are edge cases. And more importantly, we don't just want a yes or no answer. We want to know how confident the model is. Is it 51% sure or 99% sure? A straight line down the graph can't give us that. So instead, we need a model that can turn raw data into percentage or a probability. To turn that straight line into a probability, we use something called the Sigmoid function. Think of it as a mathematical squeezer. No matter what number comes out of the model, very large, very small, positive, or negative, the sigmoid compresses it into a value between 0 and 1. That's important because now we can interpret the output as probability. For example, 0.92 means the model is 92% confident you'll make it home by 6 p.m. 0.12 means it's unlikely. This curve is what allows logistic regression to move from just drawing a boundary to producing meaningful confidence scores. And once we have a probability, we can apply something called a threshold, usually 0.5 right in the middle. If the probability is above 0.5, we predict yes. If it's below 0.5, we predict no. So logistic regression isn't just a line. It's a line transformed by the sigmoid into a probability machine. But sometimes a single curve isn't enough. Real decisions aren't always smooth. They're often a series of simple questions. Think about a delivery company deciding whether to use a drone or an electric van. Instead of drawing a line, a decision tree works like this. It asks one question at a time. For example, is the delivery under 2 miles? If yes, use the drone. If no, use the van. Next question could be, is the package lightweight? And then another question could be, is it raining? Each answer moves us down a branch of the tree. And eventually, we reach the bottom called a leaf node, which gives us the final prediction. So instead of one mathematical boundary, decision trees build a structured flow of decisions. It's a model that thinks in simple rules. If this, then that. But how does the AI know which question to ask first? It uses a concept called entropy. Essentially, the AI is a neat freak. It looks for the question that sorts the data most cleanly. If weight helps split the data into clearer groups, the tree will put that question right at the top. It's all about reducing the messiness of the data. The problem is a single decision tree can be brittle. It can become too focused on small details in the data. That means it might perform well on training data, but make mistakes on new, unseen situations. To solve this, we use something more powerful, a collective, or an ensemble. Instead of relying on one tree, we build many decision trees, or an ensemble of decision trees. Each tree is trained on slightly different data. Then, when it's time to make a prediction, they all vote. For example, if 80 out of 100 trees vote to use the drone instead of the van for the delivery, the final decision becomes the drone. This idea is called a random forest, and the reason it works so well is simple. One tree can make a mistake, but a forest of trees is much more stable. By combining many models, we reduce errors and improve accuracy. It's the power of the crowd applied to machine learning. Now, there's another powerful ensemble method called gradient boosting, and it works very differently from random forest. Instead of all trees voting at the same time, they're built one after the other. Think of it like a relay race. The first racer runs the first part of the race, then they pass the baton to the next racer who builds on their progress. Similarly, the first tree makes a prediction, then we measure its mistakes. The next tree is trained specifically to focus on those errors, trying to improve where the first tree struggled. Then the third tree focuses on the remaining mistakes. And this continues step by step. Each new tree doesn't try to start from scratch, it tries to correct the weaknesses of the previous one. That's why it's called boosting, because we're gradually boosting performance by learning from errors. This sequential improvement makes gradient boosting extremely powerful, especially for complex patterns in data. And that's why algorithms like XGBoost are widely used in a real-world machine learning system. Okay, so in this video, we explored the logic behind AI decision making, also known as classification. We started with the foundation, binary classification, where the model chooses between two categories. Then we saw how logistic regression uses the sigmoid function to turn raw data into probabilities. After that, we moved to decision trees, which are models that make decisions using simple if-then rules. And finally, we looked at ensemble methods, where multiple models work together to improve accuracy and stability, from smooth possibility curves to structured decision trees to powerful model combinations. This is the core toolkit behind modern classification systems. To make it even clearer, I want you to screenshot this table for high-level understanding. Don't worry, I'll wait. Okay, so now you can see how each model fits into the bigger picture. Each one solves classification in a different way, but they all aim to turn data into decisions. And that understanding is the foundation of real machine learning. Thank you, and follow for more.